In this video, what we're going to do is we're going to deal with what are called buffer solutions. Buffers are important solutions in terms of regulating, controlling acidity or pH. And in order to produce a buffer, what we're going to do is we're going to take a weak acid, specifically a weak acid, and its conjugate base. And from that weak acid and its conjugate base, we will be able to produce a solution which is resistant to changes in pH. Okay, so let's take a look at an example or a little bit of detail here. So this is section 17.2, and this is buffers. Now, what I'm going to do to begin with is I'm going to do a little derivation here. I'm going to take an acid, and I'll write it as HA just for it to be a generic acid. There is no element A in the periodic table. So we take this acid, and acids will protonate water, right? And let's make this a weak acid. So the acid will protonate the water so that we get the conjugate base and the conjugate acid. And the conjugate acid is hydronium, right? So this is the conjugate base. And this is the conjugate acid. Now what I'm going to do is I'm going to manipulate the equilibrium expression for this. So let's write Ka for this to begin with. Okay. So we're going to do the products first. Typically people will put the hydronium first, but it doesn't really matter. Okay. So there's our expression for the equilibrium constant. Now what I'm going to do is I'm going to manipulate it, and I'm going to manipulate it by taking the log of both sides, just like we do for calculating pH. Log base 10, okay? So we're going to take the log of the Ka, and then we'll take the log of the other side as well, right? You have to take the log of both sides. Now, when you take the log of this very large expression here, the conjugate base concentration times the hydronium concentration, which is the conjugate acid, divided by the weak acid. Okay. We can use the rules of logarithms, and the rule of logarithm I'm going to use here is that the log of x times y is equal to the log of x plus the log of y. Okay. So I'm going to do that in terms of the conjugate base and the conjugate acid, those two products there. Okay. So I'm going to write this as the log of A minus over HA. Okay, so I'm going to keep that as a ratio plus the log of the conjugate base, conjugate acid, hydronium. Okay. And again, that's still equal to the log. I'm going to drop the 10. Typically, if it's LOG, it's base 10. Okay, so now what do I do? Now what I'm going to do is I'm going to multiply the equation through by minus 1. Okay. Now, the reason I'm multiplying by minus 1 is because we have this idea of pH, right? We know that pH is the negative log of the hydronium concentration. So we can substitute that in there. Sometimes people will just actually leave the brackets out just to make it a little bit easier. All right, so that becomes plus pH. But we also have this other term called pKa. Now pK is the minus log of the Ka. Same idea, just minus log. So we're going to call this pK. Oops. Okay, now what I'm going to do is I'm going to add this to both sides. Right, I added that log term to both sides. So now I have what is often referred to as the Henderson-Hasselback equation. Or the buffer equation. And it says that the pH of a mixture of a weak acid with its conjugate base. So we're putting two materials in together. The weak acid, HA, and its conjugate base, A minus, which typically, the A minus would be put in as, say, sodium or potassium salt. Right? That's usually what you would do, okay? And so this equation is a very simple way to calculate the pH of this particular mixture, which is important in terms of buffers. As I said, a buffer resists a change in acidity or a change in pH. So it's often useful to calculate the pH of a buffer. And to do that, we just need to know the pKa, the concentration of the conjugate base, and the concentration of the weak acid. If we know those three values, we can just run it through here and calculate the pH of that solution, okay? So this is used with a mixture of a weak acid and the conjugate base, its own conjugate base. So we don't use it for strong acids. So we would not have a buffer where the buffer was made out of hydrochloric acid and chloride. Okay. Slide here. So HCl and Cl minus, that's not a buffer. Why? Because this HCl is a strong acid. Now, here's one that is a weak acid. HCN is a weak acid. Okay, so I'll write the Ka value next to it. Okay, so that's a weak acid, so that's okay. But suppose I put it with chloride. That wouldn't be a buffer either, because chloride is not the conjugate base of HCN, right? You have to have the weak acid and its own conjugate base. So if I had HCN and NaCN, okay, now you got a buffer. That's okay, that's a buffer. Why? Because we have the weak acid and we have its conjugate base. Again, we don't worry about the sodium or potassium because those are just ions that are going to dissolve into the water. The sodium and potassium are conjugate acids of a strong base, so they don't affect the acidity. Okay, so that would be a buffer. Another example would be acetic acid. Acetic acid is a weak acid with a Ka of 1.8 times 10 to the minus 5. And if we were to put that with sodium acetate, that's the conjugate base right there. So good, we got the conjugate base, we got a weak acid, a mixture of those two together, that would be a buffer. And again, a buffer resists changes in pH, changes in acidity. Okay, so we have this Henderson-Hasselbalch equation. We're going to run through three different types of problems in this section. There are other types of problems as well, so you can refer to your textbook for other types of problems. But we're going to look at three relatively classic type of problems for Alex on this. Okay, so let's take a look. First one's a nice, easy one. Interconverting Ka and Pka. So I talked a little bit about Pka. Pka is an important parameter. pKa's have values that are sort of like pH, 1 or 2 or 5 or 10. So they're useful numbers for keeping in your head, right? Values that are very large or very small are not, our brains aren't really great at handling those, keeping them in our head. So for example, if I said, what's the price of something, and you said it was 1.35 times 10 to the minus 7, that would be hard for me to remember that, right? But if I said it was 4.2, I could remember that more easily, right? So the same is true for pKa. We could report Ka values, but if we want to use the Henderson-Hasselbalch equation, the pKa is a more useful value. It's just easier to put it into the equation, 4.76 or whatever, 1.8. Another reason is that it actually gives you a nice measure of how strong an acid is. So just like pH, remember, the lower a pH, the more acidic the solution is. The higher the pH, the less acidic. We can do Ka in the same way, pKa. The lower the pKa of an acid is, the stronger the acid is. So if I say an acid has a pKa of 2.5, I would know immediately that it's a stronger acid than an acid that has a pKa of 5.5, right? So the lower the value, the stronger the acid is. So that's kind of cool as well. So easier numbers to deal with. So let's take a look at this. Complete the following table, which lists information about the measured acid dissociation constants of 3 unknown weak acids. Be sure that you put the number in the table, or be sure that the number in the table that you put in the table has the correct number of significant digits. So 3 acids, A, B, C, they give us the Ka values for 2 of them. They give us the pKa for 1 of them. And then they want us to do the relative strength of them, how strong they are. So that's kind of cool. Okay. And let's take a look. Create this. So acid A, acid B, acid C. So 2 of them, they give us the Ka value, 1.04 times 10 to the minus 12. They don't give us a value for that one. And then 2 times 10 to the minus 3. So notice this one only has 1 significant digit, whereas the first one has 3. And then the next column over is pKa. And they want us to calculate the pKa for the first and the third one. For the second one, they give us the pKa. And then they want us to do the relative strength. Okay, so let's take a look. Let's do the first one. Let's do part A. The pKa, as I said, is just the negative log of the Ka. I'll put that in parentheses. Okay. So pKb would be the negative log of Kb, right? pKw would be the negative log of Kw. pH would be the negative log of H plus concentration. So all we got to do is negative log of 1.04 times 10 to the minus 12. Now I can tell you right now, the answer to this is going to be very close to 12, because remember the log base 10 is really just powers of 10. That's really what you're doing, is counting the powers of 10. So the log of 10 to the minus 12 would be minus 12. The negative of that would be plus, and you get plus. But it's a little bit more than 1.04, so it's going to be about 11.98 or something like that. So let's figure it out. So we want the log, well, minus log of 1.04 times 10 to the minus 12. And 11 point, yeah, I was right, 11.98. Okay, remember, the smaller it becomes, the smaller the Ka, the weaker the acid is, but for the pK, it's the other way. The bigger it is, the weaker it is. So let's put this over here. We can't do relative strength yet. Well, we could compare A and B because we have their pKa values, but let's do part B. So now notice with this one, we're given the reverse. We're told the pKa, and we want to find the Ka. Well, how do we do that? It's just like we did with pH and hydronium concentration. So what we do is, let's put in here, pKa is minus log of Ka. So if we want to get Ka, we have to multiply both sides by -1. So don't forget to do that first. Right, that changes the sign. And then we use the inverse function. The inverse function is 10 raised to the power. So 10 raised to the negative pKa is equal to 10 to the log of Ka, but the 10 and the log cancel each other essentially. They undo each other. So you get Ka. Okay. So all we have to do is take 10 and raise it to the negative pKa. So 5.35. Okay. So 10 to the x and then minus 5.35. And you get 4 point, it's actually 4, right? There's, oh no, we're doing the second one. There's 2 significant digits, 1, 2. Everything after the decimal point is significant, so there's 2. So 4.5 times 10 to the minus, looks like 6. Okay, so there's our value. Remember, equilibrium constants are unitless. Okay, looking good so far. And then the last one, part C, is we want to find the pKa, so we take negative log of 2 times 10 to the minus 3. Oh, that's one I can do in my head. The log of 10 to the minus 3 is minus 3. The negative of it would be plus 3, but then you'd take the log of 2, which log of 2 is 0.3. So you would subtract the point, add the 0.3, and you get 2.3. But you don't have to do these in your head, just, minus log, parentheses, 2 times 10 to the minus 3. Yep. Now that's a little tricky. There's only one significant figure here. So that means we would do 1 digit after. So just round it to 2.7. So you see, I got 2.69897, but we want one significant figure. There's only one significant figure here. So we want 1 here. So we're going to round that up to a 7, and you'd have 2.7. The 2, the number in front of the decimal point, is essentially telling you how many zeros are in the decimal number before you get to the actual numbers. Okay, so this is 2.7. So now, as I said, what happens is the relative strength works kind of like pH. The lower the value, the stronger the acid. So this one's the lowest value, so that's the strongest. This one's the highest, so it's the weakest. And then this one's in between. Okay, so as pKa goes up, strength decreases. Goes down, right? It becomes a weaker acid. Okay, be careful. That doesn't necessarily mean that it's safer is because it's a weaker acid. Hydrofluoric acid is not a real strong acid. It's not a real weak acid, but it is a weak acid. It's very dangerous because the fact that it's hydrofluoric acid is used for etching glass, so it has to be stored in plastic. Hydrofluoric, sorry. HF. So it doesn't dissolve, I mean, it doesn't dissociate because it has a Ka of, sorry, it's 10 to the minus 4. It's approximately 10 to the minus 4. And so it's not really a very strong acid at all. But what that means is that when you put it in water, it's mostly HF. There's very little H plus and very little F minus. HF can actually dissolve through the skin. And then what happens is the HF reacts with calcium that's in your blood. And so what will happen is they'll react and you get calcium fluoride, which precipitates out as a solid. Okay, they react. The calcium combines with the fluoride. So it takes calcium out of your blood. And if you take calcium out of your blood, that ends up being a very dangerous thing to do. Okay, so be careful. It's true, strong acids are dangerous, but weak acids can be dangerous as well. Okay, so there's one type of calculation. The second calculation that we're going to do here, so is just relatively basic. It's relatively simple. I don't want to use the word basic. Is that we're going to take a look at how we calculate the pH of the buffer solution. Okay. So one thing that's a little bit different about the ALEX problem here compared to most textbooks is they will give you a value of Ka. Here they give you the value of Kb, but that's just an additional step that we have to take into account. So it's not a big deal. Okay. Calculating the pH of a buffer. A solution is prepared at 25 degrees Celsius that's initially 0.11 molar in diethylamine, C2H52NH. So that's the name of a compound, diethylamine. It's a weak base, so they're telling you it's a weak base with a Kb of 1.3 times 10 to the minus 3. So there's the Kb for the weak base, right? It also has 0.11 molar diethylammonium bromide, C2H52NH2Br. That is the conjugate acid of the weak base. So that's the key to solving this problem. Calculate the pH of the solution and round your answer to 2 significant places or 2 decimal places. Okay. That means 2 digits past the decimal point. So let's go through this one and I'll show you how we identify what's going on. The most difficult part of this problem is just identifying what's what. So what they do is they tell you you have 0.11 molar diethylamine. So it's C2H52NH. Okay, now I know they put 2 pairs of parentheses in there. That was just, the outside parentheses was just to tell you that our diethylamine is this formula. The only parentheses that are important in terms of the formula are these ones that I've drawn right there. Okay, they tell you it's a weak base. Okay, so we know that's a base. Then they give us the value Kb, right? A weak base should have a value of Kb. Okay, so diethylamine, oops, sorry, that's a -3. Diethylamine is a stronger base than ammonia. Remember, ammonia NH3 is 1.8 times 10 to the minus 5, it's Kb. So this is a bigger value, 10 to the minus 3. So it's a stronger base than ammonia is. And in organic chemistry, when you take organic chemistry, if you take organic chemistry, they'll go through discussions of why it's a stronger base and that sort of thing. Okay, but you also have 0.11 molar diethylammonium bromide. Okay, and they give you the formula, C2H5. And H2. Okay, so just a reminder, bromide salts, chloride salt, let's do chloride above. Chloride, bromide, and iodide salts. Okay, All three of these are conjugate bases of strong acids. So no effect on acidity or pH. No effect on acidity means no effect on pH, right? So that means we can ignore any chlorides, bromides, or iodides in here. So that's right there. So really, let me just show you what this formula is telling us. It's really C2H52 NH2 plus. And then there's a Br minus, which will dissolve away when you put it into water. So really, if you take a look at this, what is the difference between the ammonium salt and the amine? It's just that you've added an H plus. So this is the conjugate acid of the base, right? Of this base right here, of this weak base. So there's your weak base, there's your conjugate acid. It just has an extra H plus. That's what the conjugate acid of a weak base is. It just has an extra H plus. Or another way of looking at it is a weak acid has one more H plus than its conjugate base, right? Or the base has one less hydrogen than the acid does. So those two, what I'm going to do now is I'm going to write these out as the weak acid and the weak base. So the weak acid is the C2H52NH2 plus. And then the weak base is C2H52NH with one hydrogen, no charge. Okay. So now here's what we can do. We can use this in our Henderson-Hasselbalch equation. Okay. So let me write it this way. I know I put A minus and HA here in the past when I introduced it at the beginning of this lecture. I'm going to write it a little bit differently. The base over the acid. Okay, and again, remember they have to be weak acids and weak bases, right? Okay, so here's our acid and base. They're both 0.11 molar, right? It told us that the diethylamine is 0.11, and it told us the diethyl ammonium is 0.11, so they're both 0.11. But here's one other problem. They didn't give us the pKa, they gave us the pKb. I'm sorry, they didn't even give us the pKb, they gave us the Kb. So what do? This is where we pull out of our toolbox from chapter 16. There's a relationship between Ka and Kb, right? A weak acid and its conjugate base, a weak acid, weak base, they have a Ka and a Kb related to each other. So the Ka is just Kw over Kb. So 1 times 10 to the minus 14 over 1.3 times 10 to the minus 3. Isn't that cool? So those things kind of come out a lot. So 10 to the minus 14 divided by 1.3 times 10 to the minus 3. And you get 7.7 times 10 to the minus 12. So there's our Ka. So now we can calculate pKa minus log. I wonder if my calculator will let me do it this way. Nope. Okay. So minus log, I have to enter the number in. 7.7 times 10 to the minus 12. And you get 11.1. Okay, so now we have the pKa. So now we can use the Henderson-Hasselbalch equation. Try to memorize it. 11.11 plus the log. They're both 0.11. Okay, come on. Here's why that's cool. 0.11 over 0.11 is 1. The log of 1 is 0. So this is 11.11 plus the log of 1, which is just 11.11 plus 0. You can try that with your calculator, log of 1. So it's just 11.11. And there's our answer. Okay, a relatively simple calculation. Let's take a look at another example. Okay, calculating the pH of a buffer. A solution is prepared at 25 degrees Celsius that's initially 0.084 molar in benzoic acid, a weak acid with a Ka of 6.3 times 10 to the negative 5, and 0.43 molar in potassium benzoate, KC6H5CO2. Calculate the pH of the solution, round your answer to 2 decimal places, so 2 places after the decimal point. Okay. We're going to calculate the pH. Now notice this one's actually simpler because they give us the Ka values, so we can calculate pKa directly. We don't have to go through this Ka to Kb to Ka for this one. So let's take a look. Okay. So 0.084 molar HC6H5CO2. Okay, that's a weak acid, and they give us the value of K, 6.3 times 10 to the minus 5. Okay, we're given the value of Ka. Then they give us a concentration of KC6H5CO2. Okay, now again, let's remind ourselves what's going on here. This is the weak acid, right? HA. This is the H part, this is the A part. This is Ka, right? An acid has 2 parts. It has the H and then the A. A base has a metal and then an OH, right? At least a strong acid. This is a strong base does. The salt, this is a salt. It's a potassium salt, right? Sodium or potassium. Because these are conjugate acids of strong bases, they have no effect on acidity. So they're put in the salt because they're not going to affect the acidity. So we can essentially ignore them. So this is your conjugate base right there. Okay, and this is your weak acid. So the pH is going to be your pKa, which we'll calculate. So you're going to put the base on the top. So C6H5CO2 minus. Remember, it's got a minus, right? And then you put your acid in the top. Right, this one's not negative because it's got the H plus attached to it. Now, we can calculate the pKa very easily. Minus log 6.3 times 10 to the minus 5. And then we just need to put our concentrations in. It's 0.43 over 0.084. The molarity cancel, so that's why that works out. Okay, so I'm going to go ahead and calculate the pKa first. So minus log of 6.3 times 10 to the minus 5. That's a 5, by the way. I'm sorry if it's hard to read it. And you get 4.20. And then we're going to take the log of 0.43 divided by 0.084. That doesn't make sense. 0.43 over 0.084. Oh, I see what's happening. This calculator requires me to hit it several times, or it just keeps information in there. Okay, 5.12. Okay, this ratio here is 5.12. So you're going to get 4.20 plus, let's try that, log 5.12, 0.709. So that's 4.91. 2 significant digits, 2 decimal places, okay? There you go. So I do want to make a mention about this buffer equation, which is this idea of this ratio. Okay. So it's the pKa plus the log of that ratio. So what happens is if this is larger than the one in the denominator, this one's smaller. So for example, 2/1. The log of that is positive. Okay, you get a positive value. So that means the pH will be larger than the pKa, right? So if I said, hey, this was 4.20 plus 0.3, see how it's higher? So if you have more of the conjugate base in the solution than you have the weak acid, the pH will be higher than the pKa. On the other hand, if you have A minus is smaller and HA is larger, so for example, 1/2, the log of 1/2 is negative 0.3. It's 0.3, the same number as the log of 2, but it's negative. So that means your pH is going to be 4.20 minus 0.30 or 3.9. So what happens is if you have more of the acid than you have of the base, the pH will be lower than the pKa. Okay? Lower than the pKa if you have more acid, higher than the pKa if you have more base. So that's a good way for you to check your answer. If you say, hey, the pKa is 4.2, and I get a value of 4.5 for the pH, and I see that there was more acid than base, that doesn't make sense. The pH goes higher than the pKa if there's more base. It goes lower than the pKa if there's more acid. Okay, so that's just a nice little check for you to use that equation. Okay. Now, let's take a look at one more type of question for this section. As I said, there are other types of problems, but let's take a look at this one. And this is a little bit of just sort of manipulating the Henderson-Hasselbalch equation to do a calculation. A chemistry graduate student is given 450 milliliters of 0.20 molar diethylamine. Okay, here's that diethylamine, that base, right? Diethylamine is a weak base with a Kb of 1.3 times 10 minus 3. They want to know the mass of the dimethyl ammonium bromide, C2H52NH2Br, that the student should dissolve into the solution, into the C2H52NH solution to make it a buffer with a pH of 11.04. You can assume the volume of the solution doesn't change when the diethyl ammonium bromide is dissolved in it. Be sure your answer has a unit symbol, which should be molar, or actually grams, right? We're doing grams, we're calculating mass. So there's a lot in the wording in here. There's just no way to word this more simply. So we're going to calculate the mass. Calculate the mass. What mass should the student dissolve? That would be a mass in grams, okay? So let me show you how we're going to go about this. I'm going to distill down some of the information into something that's a little bit more useful, okay? Okay, so we have 450 milliliters. That's a volume, right? 0.20 molar diethyl amine. So there's your diethylamine. They then tell us the value of Kb. Value of Kb is 1.3 times 10 to the minus 3. Okay. Now they want us to find the mass of diethyl So that's the diethyl part right there. The 2 is the di, so diethyl. Ammonium bromide dissolved to give a buffer. At least they tell you it's a buffer at pH 11.04. Okay, so we want to find the mass of the diethyl ammonium bromide that we're going to dissolve to give us a pH buffer at 11.04. Now, there's a couple of different ways to deal with the Kb, and I showed you one way before, and I'm going to show you the same way here. I'm going to do Kb, Ka times Kb equals Kw. So the Henderson-Hasselbalch equation has Ka, not Kb in it. So let's just go ahead, calculate Ka first. There's actually a different way to do it. There's a different form of the Henderson-Hasselbalch, which you could also use. So divide that by 1.3 times 10 to the minus 3. And that's an error. Oh, I see. Again, at the 10 to the minus 14 divided by 1.3 times 10 to the minus 3. Of course, we had that number earlier. 7.7 is what I put before, but I'll round it to one more digit. I'll do 3 significant figures. Okay, so there's your Ka. So now you can do your pKa. Okay. So I wish I could just sort of store this. Okay. So minus the log of 7.69 times 10 to the minus 12. And again, you get 11.11. That was earlier in our lecture, right? Okay, so now here's what I'm going to do. The pH, the Henderson-Hasselbalch equation says pH equals pKa plus the log of the base. I'll put A minus over the acid. Concentrations, moles per liter. Is that right? Moles per liter, right? Concentrations. That's what the brackets mean in this context. So notice we are told we want the pH to be 11.04. So I'm going to put that in. Okay. Now, leaving aside for what we are going to calculate here, it's pretty clear that if we're going to use the Henderson-Hasselbalch equation, we have these two numbers here. So we can get this ratio, we can get the log of that ratio out of those two numbers. Okay. We're going to come back to what it's specifically asking for, but I want you to just sort of point out at this stage, we know what the pH needs to be. They told us, and we know what the pKa is. We calculated that. So that equation allows us to calculate this ratio here. So let's take a look. We would subtract 11.11 from both sides. So you're going to get minus 0.07 is equal to the log of that ratio. And again, I'm using A minus and HA just to make it simpler. I don't want to write out, get all confused where the C's and the H's are. I'm just doing base over acid, right? Log of the base over the acid. So now how do we get rid of the log? We do 10 to the x, 10 to both sides, right? Because the log in the power of 10, base 10, they're inverse functions. So by taking 10 to both sides, we get rid of the log on the right side. So now how do we do this? We got to do 10. So there should be a function 10 to the x on your calculator. It's usually on the same button as log. So 10 to the minus 0.07. So you should get a number like 0.85. Okay, so now what I'm going to point out is that we were given the concentration of the base. right? The concentration of the base was given. It was 0.2 molar. So we know this value right there. So if we want to find the concentration of HA, it would just be the concentration of A minus over 0.851. So that would be 0.20 molar over 0.851. And that'll give us the concentration of HA. So 0.20 over 0.851 is 0.235. Okay, there's your concentration of your acid. That's not the answer. Sometimes the questions will end at that point, but we want to go a couple more steps. We're doing a mass calculation. Okay, so hopefully you see how I did that, right? 0.851 is equal to that ratio. So if we want the denominator, we have to take this one over that one. Okay. So now the concentration of HA. By the way, the concentration of HA is this one right here. That's the conjugate acid, right? That's the acid. This is the base. This is the acid. Is equal to 0.235 moles per liter, right? See how I'm writing in moles per liter? So that's equal to the moles of HA over the volume. Now, what's the volume? 450 ml. See how I made that 0.450? Why? Because 1,000 milliliters is a liter, right? So if I have 450 milliliters, 1 liter over 1,000, 0.45 liters, sorry. So 0.45, 450, okay? So now I know the molarity and I know the volume. I can find the moles. So let me just bring it down here. Moles of HA are equal to 0.235 moles per liter times 0.450 liters. Okay, so 0.235 times 0.45, and you get 0.10575 moles of your acid. We're almost there. You got the number of moles, okay? The last step is to convert that to grams. If you have the moles and you know the molar mass, you can calculate the number of grams, okay? So I have this number right here. Let me just bring this up over here so I can see it, because I'm going to come over to another slide. Okay. So the acid is C2H52NH2 plus, but we need to weigh out the salt. They're telling us to weigh it out. So we're really doing the bromide salt. Okay, that's what we're doing. And we have 0.10575 moles of C2H52 NH2Br. In order to calculate the mass, we have to convert it to grams. So we need to know the molar mass. Okay, 2 carbons times 2, so 4 times 12.01. There's 5 times 2, that's 10 plus another 2, 12 times 1.01. We've got a nitrogen, and we got a bromide. Okay, very heavy conjugate acid. So this is 48.04. Oh, I see what happened. So 48.04. Sometimes I can just do these in my head. It's easier. There we go. So plus 12.12 plus 14.01 plus 79.90, 154. grams per mole. There's your molar mass. So if I have 0.10575 moles, and I want to convert that to grams, I just multiply it by the molar mass. Okay, and there you go. So there's your answer. It's around 16.3 grams. So in this particular problem, there's a lot, right? See how we build up to that? So sometimes they're going to give you the base. Sometimes they'll give you the acid. Let me just show you. I'm not going to go over it, but I want to show you another example, and then I'll just kind of briefly talk about it. Okay, so notice with this one, 300 milliliters of 1.7 molar benzoic acid. Here they give you the concentration of the acid, and they give you Ka, right? So that means you can calculate pKa. They then tell you the pH is going to be 3.86. So again, you have the pH, you have the pKa. That means you can get the log of A minus over HA. But in this case, they gave you the concentration of HA. So you have HA in the denominator, right? So you just got to find out what A minus is. The salt of the A minus is right there, KC6H5CO2. So much of this type of problem is just sort of figuring out what information you're given and what information you're not given. So you have the molarity of the acid. You have the Ka of the acid. Okay, you're given the pH. So that means you just need to find the ratio of the base to the acid. And then once you get that ratio, that gives you the molarity of the base. You're given the volume of the solution. So molarity times volume is moles of the base. Once you've got the moles of the base, you can use its molar mass to figure out what the mass in grams is. And there you go. Okay, so very good. Good luck with this. And enjoy.